You remember a high school physics, right? Everything was so clean. A ball would fly through the air in this perfect, beautiful arc. But then you go out in the real world, you toss your keys or a wrench, and you know it's never that neat. Real things tumble, they spin, they seem to move in these incredibly complicated ways. Well, today, we're going to pull back the curtain and unravel that complexity.
So, let's start with what we know. That simple path we all learned about? That describes the motion of what physicists call a point mass. It's this ideal, imaginary object with no size where all its stuff, its mass, is packed into a single dot. It's a fantastic starting point for sure, but it's not the whole story.
Because, a real object like this wrench, it's what we'd call an extended body. It has actual size and shape. And because of that, when it moves, it's actually doing two things at once. It's traveling along a path, we call that translation, and it's spinning, or tumbling around, which we call rotation.
So how on earth do we predict the motion of something that looks so chaotic? I mean, really, is there any hope? Well, it turns out there's a trick, a really elegant way to separate the path from the tumble and look at them one by one. And it all starts by finding one very special, almost magical point inside the object. This little secret is called the center of mass.
Okay, so what is the center of mass? The textbook definition is that it's the mass-weighted average position of all the little bits that make up the object. But let's put that in plain English. Imagine you could find the single average location of all the stuff in an object. That one point, that's your center of mass.
And here's an even better way to think about it, something you can actually picture. The center of mass is the object's perfect balance point. If you could put that entire object on the tip of a pin, this is the exact spot where it would just sit there, perfectly balanced, not tipping over.
Now here is where the magic really kicks in. It doesn't matter how wildly that wrench is flipping and tumbling through the air. Its center of mass, that little balance point, it follows that same simple, predictable arc we learned about in school. It moves as if all the object's mass and all the forces, like gravity, were acting on just that one single point. And this slide just illustrates the idea so powerfully. Look at this. Even if our object explodes in midair into a bunch of pieces, the center of mass of all those fragments combined just keeps cruising along that original path like nothing even happened. Why? Because the explosion, that's an internal force. The path of the center of mass only cares about external forces, like gravity pulling it down.
So we've kind of solved the path problem, right? The center of mass takes care of the object's journey. But what about the tumble, the spin itself? Let's dive into that.
All right, so we've got a handle on describing the path. But what about the rotation? To really get a grip on that spinning, tumbling motion, we need a whole new set of tools. But here's the good news. If you understand the basics of regular, straight-line motion, you're actually already halfway there.
It turns out it's almost like there's a parallel universe. For just about every concept in linear motion, there's a direct rotational equivalent. Instead of tracking an object's position on a line, we track its angle. Instead of its linear velocity, how fast it's moving, we talk about its angular velocity, how fast it's spinning. Linear momentum has a cousin called angular momentum. And what about a push or a pull, a force? Well, its rotational twin is called torque.
So let's zoom in on that last one, torque. Because torque is the absolute key to understanding why things start spinning in the first place, or why they stop, or change how they're spinning.
In the simplest possible terms, torque is just a twist. That's it. While a force makes an object speed up or slow down in a straight line, a torque is what makes an object change its rate of spin.
You know this intuitively. Just think about opening a door. If you push right on the hinges, what happens? Nothing. You're applying a force, but there's no torque. But if you push on the handle, way out on the edge, it swings open easily. That's maximum torque. So this tells us it's not just about how hard you push, but where you push, and in what direction. So let's break it down. Torque really depends on three things. First, how much force you apply. Second, the distance from the pivot point, which we call the lever arm. Think of the distance from the hinge to the door handle. And third, the angle you push at. If you want the most twist, you've got to push hard, far away from the pivot, and at a nice right angle.
Okay, now that we have these parallel ideas for linear and rotational motion, we can talk about one of the most powerful and fundamental concepts in all of physics, conservation laws. For straight-line motion, we have this powerhouse rule, the law of conservation of linear momentum. Basically, what it says is, if you have a system of objects and no outside forces are messing with it, its total momentum, that's just its mass times its velocity, will never ever change. It's constant.
This is just like our exploding projectile, but starting from a dead stop. Here, a radium nucleus just sitting there suddenly decays, shooting out particles. Since there were no external forces, the total momentum has to stay zero, just like it started. So the particles fly off in opposite directions in such a way that their combined center of mass doesn't move one bit.
All right, so what's the spinny version of this? It's something called angular momentum. The best way to think of it is as rotational inertia. It's a measure of an object's stubbornness, its tendency to just keep on spinning exactly the way it is.
And this brings us to its rotational twin, a law that's just as important, the law of conservation of angular momentum. You guessed it, it's the same idea. If there is no net external twist or torque acting on a system, its total angular momentum is constant. It's just going to keep spinning at the same rate around the same axis forever.
Now you have absolutely seen this law in action, even if you didn't know what it was called. It's one of the most beautiful illustrations of physics. An ice skater starts to spin with her arms stretched way out. She's spinning, sure, but kind of slowly. Then she pulls her arms in tight to her body. And what happens? Bam! She starts spinning dramatically faster. So why does that happen? It's not magic, it's physics. By pulling her arms in, she changes how her mass is distributed, bringing it much closer to her axis of rotation. Now, because her angular momentum must be conserved, the friction from the ice is tiny so there's no external torque, her spin speed has to increase to make up for it. It's just a stunning demonstration.
And this isn't just some neat trick for ice skaters. This very principle is why a spinning top stands up instead of falling over. It's why a quarterback puts a tight spiral on a football, for stability. It even governs the orbits of planets around the sun. And on a cosmic scale, it's fundamental to how entire galaxies form out of spinning clouds of dust.
So, the next time you see something spinning, from a kid's toy to a planet, you'll know about the elegant physics that's keeping it all in motion. Which leaves us with one last little thing to chew on. If a spinning object wants to keep its angular momentum and maintain its axis of rotation, how exactly does that help keep a moving bicycle from tipping over? Something to think about. Thanks for watching.